Okay, welcome everyone. This is the week 5 webinar. And this webinar really is all about the most important theorem of all statistics. In fact, it's the biggie. I wouldn't even say there's a number 2. This is the theorem. And it allows us to do statistics. Otherwise, no one would do statistics. So let me talk about the plan. As always, I'll start out with any questions you might have. And then after that, we'll get into what's called sampling distributions. So you have a sample, and maybe you have another sample another day, another one another day, and you want to look at the distribution of them. So we'll talk about what those are all about. We'll talk a little about biased versus unbiased estimators. So you want your best guess for something. So if you want your best guess for the mean, you take a sample. Well, should you take the sample mean as your best guess? And we'll see. What if you want the best guess for the range? Should you take the sample range? We'll talk about that. And if it's a best guess, then we'll call it unbiased. And if it's not a best guess, then we'll call it bias. So we'll talk about some important unbiased estimators and some important biased estimators. Then we'll get into the central limit theorem for means. So the central limit theorem is the big theorem. It allows us to look at statistics and make really good good guesses, or really good plans based on our sample. So we can say, yeah, the sample is a good, here's how we can take our sample and then understand the population. And that's what statistics is all about. Then we'll look at the central limit theorem for proportions. And that's kind of the same idea, except it's for the yes/no answer instead of the quantitative answer, the question. And then quickly, we're not going to spend much time on it, but the central limit theorem for sums. Sometimes instead of the average, the total is what you care about more. And that happens, sometimes in certain cases. And I'll talk about the different cases. So that is the plan. This is, again, it's week 5. And week 5 is an odd number. So there's no exam this week, but there's something even more important than the exam, which is?
The project.
Yeah, the project. So hopefully you all are making a lot of progress on the project. This isn't the time to get started. This is the time to get finished or getting close to finished. So the idea here in terms of timeline, what I recommend is tomorrow or Wednesday, have your draft written. So you should be working with your partners and get that draft written. Then what I'll do is you'll send me the draft. Then I'll read through the draft, and projects tend to be, like probably 6 to 15 pages, depending on how much you write and how many, charts and stuff you put in and all that. So it does take me some time. So don't expect me to answer your email in 10 minutes because, reading that many pages for that many groups. And, we got 2 big classes. It doesn't happen in a half an hour. It doesn't happen in 4 hours, by the way. So I'll be doing that pretty much all the last part of this, work week, as we say. And then I'll send you a list of things, of recommendations for improvement, and take them seriously. So the whole point is that way, if you don't send me the draft and you just wait until this weekend and send me the, and submit onto Canvas your final submission, then instead of sending you recommendations that you can fix, I'll just write down things that went wrong and I'll take off points. So the idea is I want to give you that chance to not have points taken off by me looking at it and letting you know what, what's working and what, especially what's not working. I'll let you know what's not working, all the different things that you can fix. And then, later, like maybe Saturday, then you do your final submission, and the final submission is on Canvas. And you just go to the project 1 submission and you you put the, the document in, okay, and then and you hit submit. Make sure that you only need to have one submission per group. Make sure that your names are on each of your names are on the project at the beginning. So that is important so that I can give credit for everyone. And then what I do is I'll give you feedback for, let you know why I graded it the way I did, what went right, what went wrong. And then if you were the one that submitted it, then you're the one that can see the feedback. So please share it with your partners. So that's your responsibility for being the submitter, is also sharing your submission back, or my feedback back to your partners. And I'll send a note saying, please, share with your partners. And I'll also send a note to your partners saying, please ask, whoever it is that submitted for the feedback, because that's how it works. And I put the feedback directly on the paper. That's why I can't send it to everyone, because it gets put onto the paper, which only is that one submission, is the way it works. And then I give general feedback to everyone, and I just copy and paste for all of you for the general, but ones that are specific to the, on the paper, that's different. So again, the project is a big deal. Just let you know, I have, the good news is I gave a test in my face-to-face class, a very long, they had 2.5 hours, although it didn't take that long, but I was able to do all my grading today. So you have your exam graded, and your discussion posts are all graded. Take a look at my feedback on that too, because hopefully you get used to what I'm looking for. And in the webinars, I give you examples, and also on the discussion boards. And I do expect you to model those, to use those as a model when you're answering questions for the exam that are the written questions. So, that is important to keep that in mind. Keep the wording. When I say you have to have those words, or I'll take off points, I'm honest, just let you know. Okay, so they're important. And also, when you make a description of something, don't make it completely general. Make sure you relate it to whatever the topic was. So those are just some things I wanted to mention, very important. And again, a lot of you did great, by the way, but there's some of you that need to do, some more work. And just hopefully you know by now that those problems, except for the very last one this time, sometimes the last two or sometimes the last three, they come right from your homework, just randomized from the homework, So if you didn't do well, that means you're not redoing homework problems enough so that you can get used to them and do well. So make sure that before you take each exam that you do well on well, I shouldn't say homework, on your chapter assignments, I should say, because everything in this class is homework, right? Because you never come to class. I mean, it's all at home. Okay. Any questions about anything? It's a good time to ask. No? If not, then I'm going to ask you a question. And let's see, how many do we have here? Okay, we have enough. So here's the question. And the rule is you put it in the chat box. I'm not going to say your name. You have to give me an answer, but you don't have to give me an answer. For some reason, you want to keep it private, you're allowed to make something up that is reasonable. And the question is, how many hours a week do you work? And when I say work, I mean work for pay. So that does, working on the project is not work, because you're not getting paid for that. Okay, most of you are not. So how many hours do you work a week? And I want you to put down the number of hours that you work a week in the chat box. And again, if you don't feel comfortable telling everyone, you're welcome to, not give the exact number, but just some reasonable number that someone could work. But most people don't care. So 40, 32, 40, 26. Forty seems to be the most common. So everyone should put in the chat box. Any others? Okay, 0, that can happen. Okay, if you said 10,000, then you're lying because there aren't 10,000 hours in a week. Okay, I think I'll call it. Okay, so we have, and I'm doing this as an example, and I want to let you know this is way too small a sample to do anything that interesting, but I want to do it so we can understand something. All right, so that's the first thing. Then let's see if you can do the next thing. And that is, and this is, you don't put in the chat box. I want you to pick 3 random numbers between 1 and 6. And you can use your phone, you can use a computer to get random numbers out of it. So I'll just give you a minute. It shouldn't take longer. You can just ask your phone, give me 3 random numbers from 1 to 6, or you can go into the computer with the random number generator I did and that I created 1 to 6, and just get 3 of them. Okay. So again, that shouldn't take long. That should be fast. Okay, so now what I want you to do, you don't have to put in the chat box. Just have them. So this is 40 is 1, 32 is 2. The second 40 is 3, 26 is 4, 40 is, the third 40 is 5, and 0 is 6. Okay. So you have, without even maybe knowing it, you just pick 3 of these numbers randomly. Does that make sense? Okay. So next thing I want you to do, and this is where you're going to need to use the calculator. Okay. And you can go to, if you remember, the calculator is one variable statistics calculator. I want you to put the numbers into the calculator, put commas between, okay, and not like the 1, 2, 3, but you know, the 40, the 0, whatever those 3 numbers you grabbed. And I want you to find the mean and the sample standard deviation, because you grabbed a sample. You did not grab a population. You only grabbed 3 of the 6. And I want you to put those in the chat box, the mean and the standard deviation of your 3 numbers. Okay, and that might take a minute or 2. But again, you can do that using my computer, you know, standard deviation statistics calculator. One variable statistics calculator, and you just put the numbers in separated by commas and you hit calculate, and you got to click sample standard deviation and then click calculate. Okay, so just going to give you a minute to do that. And when you find the mean and the standard deviation, put it in the chat box. And if you get like a really messy standard deviation or mean, a couple decimal places is fine. Okay, so I'm gonna put in the means at least. And again, I want you all to put them in. We'll worry about the standard deviation a little bit, but I want to start with the means. So put in the chat box what the mean is and the standard deviation, especially the mean of your 3 numbers. That shouldn't take long. So pop it in the chat box. Okay, 19.3. Here's some more. 26.67. You can't get 3.333 because if you take 3 of these numbers, one could be 0, but the others are all going to be at least 26. And if you take an average of numbers that are big like that, you don't get 3.33. So it's not the mean of your random number generator numbers, but the mean of the numbers that it corresponded to here. So 24, that one works. Whoops, not there. Here. So hopefully that makes sense. So say you picked your random numbers were 2, 5, and 6. You would pick 30, 40, and 0 and find the mean and standard deviation of those three numbers, 30, 40, and 0, not 2, 5, and 6. Okay. All right. I don't want to spend all day long, so I just want to mention, again, what we have is we have a bunch of means, okay? And in the real world, instead of having, just a small group of you, let's say we ask that same survey question to maybe, 50 different college students that were randomly selected from all college students in California or something like that. And we looked at the mean of those 50 that you chose. That'll give you a mean that won't be the same as the population mean, right? Notice these means are all different, right? They're not the same. Okay. But the question is, are these means a good guess for the population mean? Okay, so are they a good guess? So if you randomly pick three numbers and you found the mean, and is that your best guess based on your randomly picked three numbers? And the answer is yes. Okay. Is it going to be the population mean? No, but it's your best guess. Do you see the difference? Usually you can't get the population mean. All you could do is get a good guess. And that's what we're going to be looking at. So what we did is we just found these are called sample means. So let me put them over here. These are the sample means of sample size 3. Because all of you picked 3 of these numbers at random and found the mean. So we have 4 different sample means. Any questions on that? Okay, one thing you can do if you want a good guess, and you've done these 4, well, if you want a good guess of the population mean, you might take the mean of these sample means. That'd probably be a better guess than any of these individuals, right? So if you think about all the different possible sample means, and there's a lot of them, even in this case, right? Even in this case, there's a lot of different sample means you could get by picking 3 random numbers. But if you picked all the different sample means, then we're looking at the population mean of the sample means. So if we took every possible sample mean and took the mean of those numbers, that's the population mean of the sample means. And the symbol we use for that, since it's a population mean of the sample means, mu for the population mean of the sample means, that's x bar. Because x bar are sample means, mu are population means. Anybody lost? Because notation can get a little confusing because it's 2 weird things. So mu sub x bar, we're going to be looking at a lot, and that is, again, the mean of all possible sample means. Any questions so far? Okay. You can also take, instead of the mean of these sample means, you could take the standard deviation of those sample means. When you have a list of numbers, right, how could you not go for the standard deviation? So we could look at the standard deviation of these sample means. Okay, and if you looked at the standard deviation of all possible sample means you could get, instead of mu sub x bar, instead of the population mean of the sample means, it will be sigma sub x bar, which is the standard deviation of all possible sample means. So let me stop for a second. Any questions on these definitions? Okay, so this is the population mean, the population standard deviation of all possible sample means. Okay, they often also call it the standard error because it's just too many words to say the population mean of all possible sample means. So they call it the standard error, and that is like the most commonly used phrase for this idea. Any questions on this? Okay, so again, this comes up a lot. Okay, so here it is in kind of words. I like to put this in because it's that important. So if we consider the collection of all possible sample means, this is its own data set. By the way, it'll have a very large sample size. Even if we started with 6 items and we're just grabbing 3, there's a lot of ways of grabbing 3 out of 6. Even that'll have a big sample size. But imagine, let's say you looked at, people in our class, okay, in our 2 sections. And there's, I don't know, 40 of you or so. And let's say you did a sample of 10. Okay, a sample of 10 out of 40. And if you look at how many different samples there are out of even 40, which isn't even that big a group, there's a lot, millions of different groups of 10 you can grab. Okay, so I'm not even going to get into the mathematics in terms of that. It's huge. We kind of saw that when we did the lottery example. We looked at how many different ways of their grabbing, 10 numbers out of 40. Remember, that was millions. Do you remember that when we did the lottery? Oh, by the way, I should mention this because it's statistics, and how could I resist? I don't know if any of you saw the news about the lottery. Okay, I think it's tomorrow night, the Powerball lottery. It's $700 and something million. And if you compute the expected value, it's actually positive right now. Okay, even the post-tax expected value is a positive expected value for the lottery. Okay, does that mean you will win the lottery if you buy a ticket? No. But if you're a lottery player once in a while, this is the good time. Okay, because it's positive expected value. That's kind of what I do. I buy like every 3 or 4 months, I'll buy a ticket or 2, and I'll wait till it gets like this. If I have time to go to the market, go to the store to buy one. Okay, so it has a positive expected value, and hopefully you all understand what that means, because that's a big piece of our statistics. Okay, so again, when you take 10 numbers out of 40, you get a huge number. You get a very, very, very large sample size of all possible sample means. Okay, and if you take if you just took even if you started with, say, how about students at UCLA, because I know we have a UCLA student in our class, and let's say you grabbed 100 students out of UCLA at random, and look at every possible group of 100. Okay, there's actually more groups of 100 out of UCLA than there are grains of sand on Earth. That's how big these things get. So don't even try to list them. Okay, we're not even going to go there. Got it? Okay, they're huge. But we can, in theory, and that's why I'm emphasizing this. This is all theory. In theory, we can talk about the average of all possible ones, even though you can never actually get it by adding them up and divided by the total, because the total is too big. Okay, and you can get the standard error, which is the standard deviation of all possible sample means. Any questions on that? Okay, next definition, the sampling distribution. So hopefully you know what the word distribution is now. What are some examples of distribution shapes that we've had in class? We've had a bunch. What are some examples of distributions? Just 1-word answers. Each example is a word. We had a whole chapter on it last week. What's some examples of distributions? Yeah, binomials one, uniforms another one. And what's the big one? You guys haven't said it yet. Normal. Okay. Those are all distributions. There's lots of different shapes of distributions, right? So if you look at the sampling distribution, and that means you're looking at all possible samples of whatever sample size you're looking at. And you can put them in a histogram or so, look at its distribution, look at its shape, and you can talk about it. Okay, and that's what the sampling distribution is. Any questions on that? I thought we'd do a little exploration. And this I coded a long time ago, but it still works. So if we start out with the distribution that's, say, uniform, let's look what the sampling distribution is. I'll let you choose. What sample size do you want to grab out of? Pick a number, 2, 9, 25, 36, or 100. Okay, 100 it is. Okay, so we're going to take 100 items. We're going to take 100 items many times. And then we're going to draw a histogram of the mean of those 100 items when you can do it many, many times. Okay. And by the way, just to let you know, I started with a mean of 200 and a standard deviation of 115.47 for this particular uniform distribution. And let's take a look. Okay. Any guess on what shape it might be? The distribution of all possible samples of size 100 out of this uniform distribution. Good old flat distribution. I don't see y'all guessing. Should we see? There it is. Okay. So this grabbed 2,500. Computers are really good at this. Good luck doing it, on your own. But the computer randomly selected 2,500 samples of size 100. It's amazing how fast a computer can do that. And then drew a histogram out of that. And look at it. What does it kind of look like? And you could do the scale if you want. That's the original.
It looks kind of like a bell.
Yeah, kind of looks bell. Normal. Normal's our word, by the way. Yeah, it looks like kind of like a normal distribution. Look at the mean. Look at mu sub x bar. And compare it to the original mu. What do you notice? It's basically the same, right? It's almost exactly 200. I mean, off by like 0.06, which is not noticeable. And look at the standard deviation. Is that the same as the original standard deviation? Not even close. But if you take this standard deviation, sigma sub x bar, which is 11.57, and multiply it by 10, what do you get? You get something really close to the original standard deviation. Do you see that? Okay, just a hint. Look at these numbers, especially 9, 25, 36, 100. What do they all have in common? This is not an accident, by the way. These four numbers, 9, 25, 36, 100. What do they all have in common? See, they're all perfect squares. 9 is 3 squared, 25 is 5 squared, 36 is 6 times 6, and 100 is 10 times 10. Okay, it's not an accident, because if I take the square root of 100, I get 10. If I multiply 10 by 11.55 or so, I get 115. Okay, and that's, again, even though this is all random, that was not some random thing that happened. Let's do it again. Okay, let's do a different distribution. Let's do I'm going to call it the Manhattan distribution. You know what I call Manhattan distribution? Kind of looks like skyscrapers, right? If you've ever been in New York. Okay, that's just, I made that up, by the way. That's not some fancy name for something, but it made sense. Okay, and like I said, that's some weird distribution, but we can take samples of sample size n, how about 36 this time, since we just did 100, and then we could draw a histogram of the sample means and see what we get. And do you think it's going to look like, you know, Manhattan, or do you think it's going to look different? Should we try? Let's try it. What does it look like? It looks normal, doesn't it? Looks normal. And by the way, the mean isn't that, it's basically rounded to the nearest whole number, is the same as the original mean. If you take this 20.25 and multiply by the square root of 36, which is 6, you get about 122. Okay, so that is going to work. And that's the big theorem of the entire of all statistics, is that if we start out with any distribution and we have a large enough sample size, and we take the sampling distribution, okay, of that sample size, then the sampling distribution will be approximately normal. The mean of the sampling distribution will be the same as the mean of the original distribution. And the standard deviation of the distribution will be the original standard deviation divided by the square root of the sample size. Okay. If instead, let's do a new distribution. How about skewed left? If instead I let n equals 2. So now I'm only going to grab 2 at random multiple times and take distribution and see what that looks like. Does that look normal? It doesn't. So this theorem about being normal only works when the sample size is pretty large. If the sample size is 2, that is really small. Okay. Any guess on our definition of large? Large enough. You might be able to guess. Here's a hint. Project 1. Yeah, more than 30. More than 30 is kind of the standard agreed upon number to say that's good enough and normal enough. Okay. So, and that's what we're going to be using in class. And that's the reason why I had you do more than 30, because that is the standard, is what you should always do. Okay. When we're talking quantitative. Okay. 2 clearly doesn't make it look normal. The mean, though, is pretty close to the same mean. Do you see that? The standard deviation, that we probably can't do in our head, because we'd had to take 97.68 and divide by the square root of 2. But it actually isn't that far from 69.5. So it turns out that the mean and standard deviation calculations still work. What doesn't work when you have a small sample size is having a normal distribution of the sampling distribution. Any questions on the idea? All right, so now it's time to state the big theorem, which I just stated, but let me mention one more thing before, since I forgot to mention it, and that is a statistic. Remember, statistics are like the mean, the first quartile, standard deviation, the minimum, etc. Those are statistics, things that you get from the sample. So a statistic is an unbiased estimator. So unbiased estimator. Maybe I should put that in red too, because that is a big part of it. So it's an unbiased estimator for a parameter. Parameter would be like the population mean instead of the sample mean. We want to estimate the population mean is the idea. And if the mean of the sampling distribution for that statistic is equal to that parameter. So we saw in our little experiment, the sample mean seemed to work. Because when we looked at the mean of all the means, we got the original population mean, or real close to it. And if you take a limit, you get the exact number. So that works. The range doesn't. And it makes sense. Okay. Think about, I like a good example is height. Okay. Think about height of college students. Got it? And let's say you took a sample of size 30 college students in California. Make them California college students. Got it? And you looked at the range of your random sample of 30, which would be the tallest person in your 30 minus in that person's height minus the shortest person's in that 30's height. Do you see that? Would that be your best guess for the range of the entire population of college students in California? The answer is no. It'd be a terrible guess. Because if you randomly pick 30 people, you might get someone that's, 6'3" or so, maybe 6'5". You might get someone who might be 4'9", okay, or maybe 5 foot. Pretty short, right? But if you think about the range in the entire California college students, there's probably a college student, the tallest student I ever had was 7'7". So there's definitely, these basketball players at UCLA. That's who it was a basketball player. So the tallest person is going to be in the mid 7s, right? And the shortest is going to be this little midget, right? Or maybe a little kid that's taken the class. Might be, 3.5 feet tall. And that range is going to be much bigger than the range of some randomly selected 30 people. Do you see that? So the range would be the sample range is a very biased estimator for the population range. You would never want to use the sample range to say that's my best guess. That's what the range is for the whole big population. Bad idea. But the mean is a good best guess. Any questions on that? Okay, the sample proportion is an unbiased estimator for the population proportion. We're going to be using that a lot. So if you do a survey of let's say 500 people in America, and you randomly select them, unbiased, so you randomly select them, then that's going to be your best guess for how all Americans think. Any questions on that? Even though it may not be perfect, but it's not likely, if you take the average of all possible, proportions, if you randomly select 1,000 people, that will give you the population proportion. And again, the math is too hard for me to prove it, but you can all trust me, hopefully. Okay. By the way, what am I not including here that we talk about all the time that I told you is really important in terms of a statistic?
Standard deviation.
Yeah, and I purposely left it out. I'll say it, but I don't want to write it down. Standard deviation is it's slightly biased. It turns out it's very slightly biased. If your sample size is large, it's like biased by not even 1%. Okay, there's a slight bias, but it's so small I wouldn't test you on it. Okay, does that make sense? Whereas the sample range is highly biased. Okay, by the way, the minimum would be highly biased, so would the maximum for the same reason. Okay, so the main things is the mean and the proportion, those are unbiased. And that's what we're going to use all the time. Okay, now comes the theorem of this entire course. Not the day, the entire course. And by the way, if you take if you take advanced statistics, in upper division, this is still the biggest theorem. Okay. When I took this one in, an upper division math class, this was the biggest theorem. The difference is we had to prove it. You don't have to prove it. You just have to believe it. Sound good? And here comes the central limit theorem. And this is a central limit theorem for means. And it says the sampling distribution for sample means from sample size n has mu sub x bar equals mu. And again, when we did that little exploration, we saw that. So the mean of all the possible sample means is equal to the population mean. Another way of saying this in words is the sample mean is an unbiased estimator for the population mean. Because that's another way of saying that equation. And the standard deviation of all possible sample means, standard error, sigma sub x bar, is equal to sigma over the square root of n. Any questions on that? Any questions? Okay. And then number two, very important number two. If the population's distribution is normal, or if the sample size is large, and our definition in our class, large is greater than 30, okay, that usually gives you one good decimal place of accuracy, okay, one significant digit of accuracy. But for our class, we're just going to say that's large enough. Okay, and by the way, this for means, this is only for quantitative survey questions, not for the yes/no questions. Then the sampling distribution for the mean is also approximately normal. So that's really important. It means that if you start out with whatever we started out with, but you have a large enough sample, then we can use the normal distribution. Okay, this original normal doesn't happen very often, but the sample size over 30, that happens all the time. Most samples are greater than 30. Okay, when you do any kind of good research, you should be over 30 in terms of number of people you survey or number of things you experiment on, whatever it might be. Okay, greater than 30. Any questions on this? Okay, so the next thing I'm going to talk about is something that has I've made probably over $100,000 on this idea. Okay, and you can too. So this is a life skill I'm about to give you. Okay, I mean, it's good for the class too, but it really is a life skill. All right, so if you, let's say you have $10,000, okay, and hopefully if you're a college student, one of the reasons you might be a college student is so you get a good job and make money. You know, maybe none of you care about money, but you know, and by the way, I'm a teacher. I don't make millions. Okay, it's not what I'm, you know, I could make a lot more money in other fields, but teaching, I make enough that I can live, but actually I make something in a much deeper way and a lot more money sometimes. And I'm talking about it now. Okay. So the probability that you're going to end up losing money after 1 year, if you put a $10,000 into the bank, okay, and by the way, the bank, that would be like Bank of America or US Bank or, you know, one of the big banks, Wells Fargo, any of those big banks. Why is the probability that X is less than 0 equals 0? Why is the probability of losing money 0? And this is not a math question. This is a economics question or a political science question. Government problem. Something called FDIC insured. Have you heard of that? That is, if the bank goes bankrupt and they have no money to give you, the government will give you money. So if you didn't know that, you know that now. You have a 0 probability of losing money. Okay. And you're going to get your interest. Who knows? I'm going to let you guess because I actually haven't looked in a long time. What's the interest of a bank account nowadays? I'm okay. You don't have to know it. Just guess. It's not 100, not 90% or anything. It's not that much. What do you think a bank account's interest is? 0.5 to 3. Okay. Let's call it, how about 1%? Sound good? So that'd be a 1% interest. Okay, so what that says is if you put $10,000 in the bank, then the next year, you're going to have $10,000 plus 1%. Okay, which by the way would be $10,100 when you see what you have, which is good, right? And you're guaranteed that you will not lose money. Any questions on that? Is that the only choice you have if you have $10,000 and you're not going to need it for a year? What are other choices you might have? Yeah, you can invest. So let's say you put it in a stock. By the way, do you think the average stock goes up 1% a year? Definitely not. So let me show you. Okay, so now you put $10,000 into a randomly selected stock. Okay, the mean, by the way, is 9%. But the standard deviation is about 20%. Okay, stock goes up and down. Hopefully you know that, right? Okay, we're going to assume stock returns are normally distributed. It's not perfect, but it's not that far from the truth. What is the probability you're going to end up losing money? Any questions on the idea? What's the probability you're going to lose money? The way you're going to lose money, by the way, is if your return is negative, is less than 0, right? If your return is less than 0, that means you've lost money. That's how money works, right? If your return is greater than 0, you gained money. Is that clear? Okay, so let's take a look. And let's go ahead. We're going to go to our calculator. Not this one. We were told we're assuming it's a normal distribution, so I'm going to get a normal probability. And the low is negative 99999. That means you really lost, right? Okay, the high is 0. Anything between negative 99999 and 0 means you lost money. Does that make sense? Any questions on that? The mean, if you remember, was 9%. And the standard deviation was 20%. Okay. By the way, it doesn't matter whether you put in $10,000 or $50,000. If that's your mean and standard deviation, the lose money has nothing to do with how much you put in. It has to do with the mean and standard deviation of the percent change. Okay. And hit calculate. Oh, sorry, I missed. There we go. I hit calculate. And there's about a 33% chance of losing money. What do you think? Is that okay? What's your thoughts? Do you think it's okay to have about a 33% chance of losing money?
No.
Okay. So I'm going to say something different. Okay. It depends. It depends. Okay. If this $10,000 is to support yourself in college, then the answer is definitely no. 32% chance is way too high a percent chance to have to drop out of college because you lost money in the stock market. Does that make sense? On the other hand, I have money called play money. I call it play money. It means that if I lose it, it's not going to destroy me. Does that make sense? And then it might be worth it. And by the way, that's a chance of losing money. If you want to gain, let's say 15%, then it's not that small a chance either. You might get a lot. Do you see that? That's why I call it play money. And you can make money with play money. Does that make sense? Is that the only choice for investing? Are there other ways to invest? And if you can't think of it, that's okay. Because again, you may not be used to investing, but again, I'm trying to show you life skill. Life skill once you have, decent money, not millions, but thousands. Okay. And here comes the next. You've probably heard of the Dow Jones Index Fund, right? Okay. The Dow Jones Index Fund is basically you put the money into an index fund. That money goes into a bunch of stocks, not one. And the Dow Jones it turns out to be 30 stocks. Okay. So if you put it into the Dow Jones, and we're going to assume, which isn't a great assumption, by the way, that the stocks are independent of each other. And they're not really independent. So by the way, I'd have to do many hours of talking about how to make it just right to have, really good investment. But I've been doing it most of my life. What is the probability of losing money now? Okay. And again, we're going to assume the Dow Jones is a representative sample and the stocks are independent of each other. We're also going to keep this mu as 9%. And I think I wrote 0.09, but I think we're using 9 now. And sigma is 20. Okay. Well, now things are different because now we're talking about an average of 30 stocks. So now we're within sampling distribution idea and not individual stocks. So if you look at sampling distribution, now we can talk about, instead of the distribution of X, we're going to look at the distribution of X bar. It's the distribution of all possible groups of 30 stocks. And that is going to be approximately normal, even though it's not quite over 30, but we're going to go for it. Okay. The mean will be 9 because the central limit theorem says the mean doesn't change. The standard deviation, on the other hand, changes. Standard deviation now is going to be sigma over root n. That was the formula for the central limit theorem. Remember, sigma over root n is 30 because there's 30 stocks that we're buying. Okay, or we're going into this fund, and then the fund manager puts it into 30 stocks. And we have a new standard deviation of 3.65. So now we can go ahead and basically we're doing the same thing, but now we have a new standard deviation of 3.65. Rounded to 2 decimal places. Everything else is the same, nothing changed. And now when we calculate it, now we have less than 1% chance of losing money. Okay, this doesn't work in 1 year, but it does work in many years. So if you're looking at, say, a retirement account, and let's say you're 25 years old, and now we're looking at 40 years of investing, and you put it into an index fund over 40 years, this actually works. And instead of putting in the bank where you're going to get your 1% interest, now we're getting a 9% interest. Do you see the difference? By the way, if you put it into the bank, okay, and get 1% interest, what do you think the bank does with your money? They do 2 things with it, actually. They loan it to people, but then if they can't find enough people to loan it to, they put it in the stock market and other investments like that. And they make the 9%, you make the 1%, and they get a profit of 8%. See how that works? So you could let the bank, use your money, or you can make money. Okay. And again, I've been doing this for several decades. I'm not that young. And is it consistent every year? No, there's been bad years, but over my over 40 years of investing now, I've made a lot of money. And later on, I'll show you other ways I make even more money in the market with statistics. Okay. And that's the key. If you want to put it in money that's going to make you money instead of give it to someone who's going to hold it for you. And then they're going to give you back the same money you started with, plus a tiny nothing. Any questions on this idea? So this central limit theorem is a big deal, but you have to know how to use it. And again, this whole, everything has to be independent of each other. What do they call that in economics? And you've all heard the word, but you may not have put it together with statistics. For all of them, for them to be independent, the different stocks are independent, or the different investments are independent. There's a word for it. Starts with a D. I don't see you all jumping in, so I might. Diversified investment. So when they say you have a diversified investment, that means that you're investments that you're putting in a bunch of places, they're independent of each other, and then you can really rely on this mean with a low standard deviation by the central limit theorem. But when you hear diversified investment, that's what they're talking about. They're talking about the central limit theorem. They're talking about this independence idea. And again, I don't have time to, do all the economics, but trust me, it works. Okay. And I mean, personally, trust me. And I've made I'm not a billionaire because I don't care about being a billionaire. I do too much, I spend a lot of my time just helping others if I can, being on Boys and Girls Club board and things like that. Helping out kids is the big thing I do. But I also have a very nice retirement fund. So I'm fine. And my daughter didn't have to pay for any of her college because I was able to, my investments were strong enough that I was able to pay for it. And my salary is not that high. It's not because I make a lot of money. Just let you know. Okay, any questions before we move on to the next topic? Okay, one more thing to look at. What if you wanted your standard error to be equal to 0.01? How big a sample would you now need if we started with a 9? It started with a 20 standard deviation, sorry. Any idea how to do that? So we put it in the formula. So let's go to, so what we want is we want n over sigma over root n. Sigma is 20. Over the square root of n. We want that to be equal to 0.01. So I can multiply by root n. And I get 0.01 times root n. Is equal to 20. Any questions on that? Just multiply left and right by root n. I could divide by 0.01. And if I divide by 0.01, I get root n is equal to 20 over 0.01. That's the same as adding 2 zeros to that 20. So 2000. Okay. Any questions on that? Okay. So now what I need to do is I need to square both sides. And you're going to get 4 million. So it'd be huge. Good luck getting 0.01. Any questions on the math there? Just a little bit of math before I move on. Okay. Next is the central limit theorem for proportions. Very important, by the way. So it's the next biggie. And it's still a central limit theorem because it's kind of similar to what we just did. And it says, let's suppose P is the population proportion. I want to mention something kind of important. I'm going to give you a little history. And it's my own. I've been teaching statistics for like a very long time. When I first taught statistics, they did it kind of like, they did proportions kind of like means. With means, they use the Greek letter for the mean, for the population mean, right? Mu. And then they used good old fashioned alphabet for X bar basically for the mean of the sample. And they used to do the same for proportions, but it confused the hell out of everybody. What is the Greek letter for P? You all know it. That's a hint. It's the only Greek letter that just about every adult knows. When I tell you, you'll say, of course. Pi. And it confused the hell out of everyone because they all thought 3.14 every time I wrote pi. Okay, so it's just not me that did it. This is like the whole country decided it didn't work. So instead, they changed the symbolism. So I want to tell you how the symbolism now works. And that is we use P and this little thing here. The way you read this, you'll love it because it's so easy to understand. You read it as P hat. That's how you read this thing. P hat, because it's got a little hat on top. The hardest part, by the way, is to type it. Typing this sucker in a computer is really hard. So if you write P hat, that's good enough if you're writing some explanation of something. So just PHAT, unless you want to do some computer programming, and then you can write that. I'll be writing this, but you don't have to. Okay. Whereas P without the hat on top of it is the population proportion. Just to note, Q is 1 minus P. So the way I like to remember that is that if P is, let's say, the proportion of people with of adults with a college education, then Q is the proportion of adults without a college education. It's 1 minus that because it's the rule of complements. Okay. So that's just a note for symbols. And what the central limit theorem says is one, if the sampling distribution for sample proportions from sample size n, it has the population mean of all possible sample proportions, that's mu sub p hat, is equal to the population proportion. Another way of saying that is the sample proportion is an unbiased estimator for the population proportion. It's a good best guess. If you take a sample and you have an unbiased sample, then the sample proportion is a best guess for the population proportion. Doesn't mean it is the population proportion, but if you look at all the different sample proportions and add them up, divide by how many you've added, then that'll give you P. Okay, and then sigma sub P hat is equal to the square root of PQ over N. And again, I like to think of P as a proportion of yes answers, Q is a proportion of no answers. N is the sample size. Any questions on number 1 for the central limit theorem for proportions? One big thing is that if you look at the sigma sub P hat, the square root of N is in the denominator. So it has that same important piece where the bigger sample you have, the smaller the sigma sub P hat is, which means that you're much more likely to be close to P in your P hat. Because remember, sigma sub P hat is how much it varies from the mean, and the mean is P. Okay, now comes a big deal. All right, if NP, and that's the predicted number of yes answers. If let's say there were 30% people saying yes, and you ask 200 people, then there'd be 60 people that said yes. That's N times P. And NQ are the number of people saying no, by the way. If they're both larger than 5, not 30, 5, and it's not N bigger than 5, it's NP and NQ, both being bigger than 5, then the sampling distribution is approximately normal. Okay. Any questions on this big deal? If it's normal, then we can compute probability. If it's not normal, we have no clue. But if we have a normal distribution, then you can use a normal calculator every time. All right. Here's what I would need you to do. Get out a pencil and paper, all of you. And I want you to write this down. For a yes, no answer, I will not use the number 30 to see if the sample size is large enough. It is a mistake usually like half of all students make. And I take off points if you make that mistake, by the way. So do not make this mistake. If it's a yes, no survey question, don't even think about the number 30. Okay, then we look to see what's the predicted number of yeses, what's the predicted number of no's. Are they both bigger than 5? If the sample size is 100, that doesn't mean it's large enough, right? So if I did a survey asking, let's say, Americans, have you been to Somalia? Okay. Well, the problem is P is going to be really small. My guess, maybe I'm wrong. My guess is none of you have been to Somalia, right? It's not a place you're trying to take a vacation in, right? Bad idea. Okay. You can have such a small P that your NP needs to be really big for N times P to be bigger than 5. Because if only, let's say, 1 in 10,000 people have been to Somalia in America, of Americans have been to Somalia, then you're going to have to survey over 5,000 people for a large enough sample size. Do you see that? Because 1 in 10,000 times 5,000 is 5. So when you have a very rare case, then you have to make sure that you have a very large sample size. One of the reasons why in project 2, just let you know, you have to use quantitative is it turns out that you need large sample sizes for any good information when you have proportions. And we'll get into that a little more next week, actually. So they're very important. All right, so the next thing, here's a question I have. That is, do a majority of women younger than 50 years old, okay, so adult women younger than 50, who have used dating sites or apps, do the majority of them, have they received unwanted sexually explicit messages or images on these platforms? Okay. Any questions on the question? Okay. Is there any way you could know for sure, complete certainty, whether the majority have or haven't? The answer is no. Because you would have to ask every single person who's ever used a dating site, every woman, sorry, who is younger than 50. And you're never going to be able to get them all. Do you see that? It's not possible. You're never going to be able to know for sure. But what you can do is you can do a sample and not say I'm sure, but say I'm pretty sure. Do you see? Which is different than being sure. And statistics is all about being pretty sure. Okay, I know it sounds weird, but that's really what it's about. Okay, and by the way, in case you're interested, there's a link that goes to it, but we don't need it because I put it in. So it took me a lot of work actually to find it. But there was a survey of 872 women that were younger than 50. Okay, I found that, I believe, I think I found that on Pew, actually. I think I originally looked at Gallup and it wasn't good. I found that on a Pew site. And of those women that they researched with an unbiased study, 56% said yes. Any questions on that so far? Okay, so 56% yes. Is that a majority, by the way? 56%? Yeah. A majority is anything over 50%, including 50.01 or something. Okay, so that's a majority. Can we say, hey, we know it. Majority of all women who have who are younger than 50, who have used dating apps, have received unwanted sexually explicit messages or images on these platforms. Can we say that because we got 56%? The answer is no. Because we only asked 872 women. We don't know about all women in America. We only know about these women. Do you see that? Any questions on the idea so far? So we can't be sure that a majority. But here's the thing, is 56% a lot bigger than 50%? Or a little bigger? And that is all about the standard deviation or the standard error. If the standard error is really small, like say 0.5%, then this really is a lot bigger. If the standard error is big, like 10%, then this is not a lot bigger. Okay, because the standard error tells you how much this might be off by. That's what a standard error is all about. Okay, so now let me show you how we're going to do this in a couple weeks, but I'm kind of doing a looking in advance right now. So if 50% of all women who are younger than 50 who have used dating sites or apps have received unwanted sexually exclusive messages. So let's say it's not the majority, but it's the highest number up to the majority, just below it, which is exactly 50%. Do you see? So if that's true, then would it be really rare to get 56% out of 872 randomly selected women younger than 50 who've used dating sites? Okay, so what's the probability that a randomly selected 872 women younger than 50 who have used dating sites or apps? So what's the probability that if we randomly selected 872 of them, at least 56%, because that's what we got, have received unwanted sexually explicit messages or images on these platforms? Any questions on that? So I'm going to slow down a little bit because this is a lot to absorb. Okay, so the idea is we want to find out how rare it would be to get what we got, because we got 56%. Is that like would be really rare if that assumption of 50% were really true, or is it not so rare? If it's really rare, then we're going to say, yeah, I'm not going to believe this 50%. It's kind of like if I flipped a coin 1,000 times and I got 999 heads, what are you going to tell me? You can tell me I'm cheating, right? Okay. Is it possible I can get 999 heads? It is, but it's so rare, you're going to say I'm cheating. Do you see that? And that's kind of what this is all about. And that's what pretty much the rest of the course is all about, is being able to look at something like that and say, you know what? It's so rare. I don't believe you. Do you see? So the you is the person saying that it's only 50%. It's not a majority. Okay. Any questions on this? Okay, so if we take NP is 872 times 0.5. So notice N was 872 because that was our sample size. 0.5 because that's our 50%, that we're making the assumption that our population proportion is 50%. And if we look at that, we get 436. NQ is, N is 872, Q is 1 minus 0.5, which just happens to be 0.5. Those numbers won't always be the same, but they will be if you start with 0.5. If we start with 0.4, you'd have 0.6 over here. And we get 436. These are both much bigger than 5. Do you agree? So that means this whole normal distribution, no assumptions needed. This is like as strongly normal as you can imagine, because it's so much bigger. These are so much bigger than 5. So normality is not a problem. Then we can use the central limit theorem and say that our p hat, so the sample proportion, if you look at all possible sample proportions, we know they are normally distributed because NP and NQ are both bigger than 5. So that means we can say that they're normally distributed. And then by assumption, our mean is 0.5, because that's what we're assuming. We're assuming it was 0.5, 50%. And our standard deviation is going to be the square root of 0.5 times 0.5 over 872. P is 0.5, Q is also 0.5 in this case. And then N was 872, take a square root. That was, if you remember, that was that formula right there. The square root of PQ over N. Any questions on that so far? Okay. Our low is, I think around 50, it should be 56, sorry, 0.56. High is 1. Okay, you could put 99999, that works too. But you really can't get over 100%. Does that make sense? You can't have over 100% of the women having had issues, because over 100% never happens. Okay, no matter what you're talking about. And then we can go to our normal distribution calculator. Let me, I like to show you how to do this. If I hit refresh, it erases everything. That way I don't have to erase. Okay, the low again was 0.56. The high was 1, or 9999, whatever you want to use. They both work. The mean was 0.5. Standard deviation, I need the calculator. That was the square root of a fraction. And that fraction was 0.5 times 0.5 divided by, and again, we're divided by 872. And it's 0.016932, etc. Just grab a bunch of them. And there's our standard deviation. Any questions on that? Is that clear so far?
Where'd you get 0.56 again?
0.5? 0.56?
0.5. Yeah.
That came from the question.
Oh, okay.
We want to see how rare it would be to get this 56%, which is what Pew got. Do you see?
Yeah. Yeah.
Right? Given this assumption, we want to find if this assumption is reasonable or not. And if it would be very rare to get this 56%, then the assumption is unreasonable.
Okay.
That was the survey gave the 56%. I didn't do any calculations. Okay. And then I hit calculate. And what do we have? P equals 0.000197. Okay, as a probability. Is that rare or is not rare, by the way? Oh, you thought we subtract for the standard deviation instead of multiply? In the formula, there's no subtraction here. Do you see? It's square root of PQ divided by N. P was 0.5, Q is 1 minus 0.5, which is 0.5. And M was that number, I keep forgetting the number, 872. Yeah, so there's no subtraction in the formula. So literally I just used that formula. And I put it in red to let you know it's an important formula. Okay. So what do you think? Rare or not rare? Yeah, this is very rare. Okay. There's like what there's like less than 1 in 1,000 chances, like close to 2 in 10,000 chances of this happening randomly. And that would be like, I don't think the 0.5 assumption could be right. Do you see how that works? Really, that's what this is all about. Okay, you're not going to see too much of it in chapter 7, but I want to give you a kind of a little preview of our future. 2 weeks from now is the future. And then we're going to spend the entire rest of the course doing this. But I want to kind of show you how this works. We'll have a calculator that does everything in one shot, but I wanted to kind of show you what this is all about. This is what it's all about. Any questions on this example? Okay. So the last thing to talk about, since we got a little more time, is a central limit theorem for sums. Let me there. The central limit theorem for sums. There are some, when do you think give me an example where you might care more about sums than the mean? And you meaning someone, you know. And sum means add them all up instead of add them all up and divide by the total. Because the mean is divided by the total. I don't see y'all jumping in, so let me tell you. So let's suppose you own a business. You care about how much money, total money you're getting, not on the average amount of money that your customers are spending. You want to find out how much money you're getting. Do you see that? The sum is how much money you get at the end of the day. The average is the mean is the average amount per customer. But you care more about how much you're getting at the end of the day than you do average per customer, don't you? Right? Because it's all about how much at the end of the day. That's business. Does that make sense? Okay, so that's one example. There are other examples. Climate change, if you look at CO2 emissions, it's a total amount of emissions that matter, not the average per country or something. Do you see that? You want to find out the total amount of emissions of CO2 because that'll tell you how much global warming, how bad global warming is going to be after doing a lot of science, by the way. Okay. So there are examples where sum is really more important than the mean. So here's what it says. And that is a sampling distribution for sums. That's like the total instead of the mean from samples of size n has mu sub. You may not have seen this symbol, but those who have, you might remember that represents the sum. And here's what's really darn confusing. Do you know how to say that symbol? It's a Greek letter, by the way. It's sigma. Confusing as hell. It's capital sigma instead of lowercase sigma. So the Greeks, just like our alphabet, they have capital letters and lowercase letters. So their capital sigma looks like this. Their lowercase sigma looks like this. And in statistics, we use them for different things. So sorry about that. Don't get mad at me. Don't shoot the messenger. It's what everyone in the world uses, so I have to use it. So mu sub summation of x is equal to n mu. And that makes sense because if you take mu, that's the mean. That's add them up, divide by n. If you multiply by the n, then it's just add them up. Do you see? It cancels the n's. And then sigma, I should say lowercase sigma, sub capital sigma x. So the standard deviation of all possible sums from samples is equal to the population standard deviation times the square root of the sample size. There's math involved. I think I'm not going to get into it, but you're welcome to look it up. It's in the book, I think, where they do the formula and calculation. It's not that bad. Okay. And then second, the good news is it's exactly the same as means. If the population distribution is normal, or if the sample size is large, greater than 30, then the sampling distribution for sums is also normal. Okay, and by the way, you have a choice. You can trust me in all this, or you could become a math major. You choose. Because that's what you need to be able to understand all this stuff fully in terms of why it's true. But trusting me works. Okay, but it does. Okay, and I didn't develop all this, but I did have to prove it when I took the advanced classes. But I wasn't the first to prove it. It's just like a homework problem for me that I had to do. Okay, sometimes we'll write this capital sigma, which means the sum is normally distributed. So if you look at all the possible sums, that they're normally distributed with mean n times the population mean, standard deviation sigma times the square root of n. Any questions on that? Okay, so here's an example. And because I knew we wouldn't have that much time, I'm going to go kind of fast because this is the least important of our three things, by the way. The other two come up all the time. This comes up maybe once or twice this chapter, then we won't do it again. So suppose the average customer at a restaurant spends $33.23. And the standard deviation is $9.22. If 65 customers eat at the restaurant today, what is the probability that the total revenue for the restaurant will be less than $2,000? Okay, and what is the first quartile for the total revenue for a day? Okay, these kind of things are real important if you're a manager at a restaurant. Do you see that? If you're doing any business, you got to know this stuff. This is important because it tells you how much you have to have in stock in your bank account, for example, so you don't go bankrupt. Okay, first quartile is important to know what a typical day is going to be, what a low day is going to be. So what we can do is we can use this big formula and say that our sums are approximately normally distributed. Okay, notice 65 is greater than 30. Greater than 30 is big enough to say we have normal distribution. Okay, and I should mention something I forgot to mention. Here we don't have to assume we have a normal distribution, because if you have over 65, you have a normal distribution. I mean, over 30, sorry. If you don't have over 30, you don't know you have a normal distribution, and you have to assume you have a normal distribution. By the way, in the real world, is it good to have to assume something? No, what are the first three letters of the word assume? Yeah, exactly. In fact, a lot of people say assume means you're making an ass out of you and me, because that's how you read assume. Okay, you never want to have to assume anything, and that's why greater than 30 is important. Okay, so assuming is bad. Okay, doesn't mean it won't happen in this class, usually because I don't want to make you like type in too many numbers. It takes all day long to type in 65 numbers, for example. Okay, so sigma, this capital sigma, is normally distributed. I take n, which is 65, times our mu, which is 33.23. I take our so n times mu, and then our sigma, so capital sigma is our original standard deviation, 9.22, times the square root of the sample size, or the square root of 65. If we want the probability that's less than 2,000, then low is a bunch of nines with a negative. The high is 2,000. Normal, so we can use this calculator now. Okay, and maybe I should do it so I can show you how to do it. We're on a new one, so let's do that. So the low is negative a bunch of nines. Okay. By the way, I pushed the 9, just held it, let it go for a while. You don't have to do that many nines, but it was easy enough. The high was 2,000. The mean again is 65 times 33.23. I think I can copy and paste it in the calculator. Let's see. There we go. 2159.95. The standard deviation was 9.22 times root 65. (9.22) times square root of 65 is 74.33 and a bunch of things. So I'll copy and paste it in. And there's the probability, 0.0157 about. Okay. So there's my probability. Any questions on that? Okay, we also want the first quartile. So the first quartile, we've done a lot of our work already. What changes?
The P.
Yep, the P. What should the P be if you want the first quartile?
0.25.
0.25. What do I leave blank? If I hit calculate, by the way, it says, please leave one of those boxes blank. So we got to leave something blank. The high. Right? Most of you did this for the discussion assignment last week, right? Yeah, it's the same kind of thing. Now I can calculate it. And the first quartile is about 2110 if you round to the nearest whole number. And that'd be the first quartile. Any questions on that? Okay, that makes sense. Okay, so that means that, 25% of times when you have 65 customers, 25% of the time you're going to be less than $2,110 in total revenue. That's what that says. And 75%, you'll be more than that money. Any questions on the central limit theorem for sums? What's the last thing to do?
Secret word.
And there it is. So the secret word is root. Because when we did the central limit theorem, whether you did sums, proportions, or means, there was a square root in that standard error. Sigma over root n, if you remember, had that square root of PQ over n, or if you remember, there was a sigma times root n for sums. So all of them had a root in their standard error formula. So the secret word is root. Okay, so that's about all I have to say. So what I think I'm going to do is I'm going to stop the recording and then unshare. And then I always like to answer any questions. It's just about, I always try and end it around 1.5 hour-ish. That's my goal. And go and end, and then you could ask as many questions as you want. So let me stop the recording. Always takes a minute.